Hello there. This is the first video in a three-part series about chaos animation. In this series, we'll explore the math and programming behind animating such systems. In this video, we'll discuss logistic maps in particular. A chaotic system is one that has sensitive dependence on initial states. Despite being governed by deterministic laws, they exhibit unpredictable and complex behavior. A rather infamous example of this system is the three-body problem. After the physicist Isaac Newton formulated his laws of motion and universal gravitation, he was guided to the stars by his contemporary astronomers. He found that two bodies could be modeled precisely, but adding a third one led to instability. This is a dynamical system that we now define as chaos. But why should we study chaotic systems? Most real-world phenomena are best represented by such schemes. How do you think that the weather is predicted? Are there equations that predict the complex movements of the clouds and atmosphere? The simple answer is no. Weather forecasters instead use large models that run on supercomputers to simulate various different conditions to attempt and predict accurate data. This can only be successfully done for up to a week in advance. The data needed to keep up with the chaotic models is simply not there. Chaotic systems are very hot in the world of cryptography. The systems that we'll study can have the application of pseudo-random number generation. This will allow cybersecurity admin to generate difficult passwords that computers can remember, but hackers won't. Lastly, population and economic models use such systems to understand how different factors affect their dynamics. For example, what will happen to a deeply interconnected ecosystem if a new predator is introduced? How would the population respond to a new food source? The two models we'll study are quite similar to each other. The first is the bifurcation map. Let's say that you have a value x. You can apply the following equation to generate new values of x for a given value of r. You then use this new value as the initial x, and repeat the process. For the first 100 iterations, you'll find that x for a given value of r is an oscillating function, as shown in the graph below. This, of course, needs to be ignored by our program. You can now store these generated values of x after 100 iterations for each value of r, from 1 to 4, with steps of 1,000th to create the following interactive logistic map. This graph has panning and zoom options, as well as a figure save feature when you're done exploring its intricacies. In the beginning, you might notice that values of x have very little dependence on the value of r, with a predictable logarithmic correlation. However, around r is equal to 3, the x value splits in two, both having some correlation, continuing until r is equal to 3.55. This phenomenon is known as periodic doubling. After this, the system turns chaotic, with values of x varying wildly to small changes in r. It's worth mentioning that there's a brief instant of stability known as a periodic window when r is about equal to 3.7. The second model we'll study is the Henon map. You'll find that it's quite similar to bifurcation. The process goes something like this. Let's say that you have two values, x and y. You can apply the following equation to generate new values of x and y based on given parameters a and b. You can then use these new values as initial values and repeat the process, just like in the bifurcation equation. Strangely, however, as the iterations continue for a is equal to 1.4 and b is equal to 0.3, the values of x and y start to populate into a specific shape as shown below. One can animate the formation of this so-called strange attractor by changing values of a while performing the necessary x and y calculations. You can then create a logistic map, similar to the bifurcation map we saw earlier, by plotting x versus a. The periodic doubling, chaos, and periodic window are all apparent. Thank you for making it to the end of the video. All the graphs and animations used in this video were generated using Python. I have linked the source code in the description for those of you who are interested. That being said, please like and share this video. Subscribe if you enjoy and would like to see more of this type of content. Goodbye.